Andrew Wiles will talk to us about curves of genus 1.
First, let me say that everything I say that's original is joint work with Cipriani. So I want to talk about a very classical problem. Abel in 1826 showed that the generic polynomial with rational coefficients with degree greater than or equal to 5 may not have solutions in radicals, that is, by extracting roots. And it's well known, Galois, in his memoir in 1846, related the solvability in radicals to the solvability in terms of the Galois group. So we can say fx may not have roots in a solvable extension. Another way of formulating it.
Are you sure about the date for Galois? It seems late to me.
Oh dear. Well, this is the date of the publication, yeah. Yes,
Who was the referee?
I think it was Cauchy, actually, wasn't it? Well, okay. So the question I want to talk about is, supposing you have polynomial in two variables, is the same thing true? Does it always have roots in a solvable equation, solvable extension, or are there examples where they don't? So Ambrose Paul has observed that for g equals 0, 2, 3, and 4, the answer is yes. There are solvable points.
What is G?
Genus, sorry. Yeah, I want to switch now, should have said. So now I'm going to switch to the language of curves, so I'll consider x, curve over q, which I'll assume is smooth projective curve, genus G, and the answer is yes.
The answer to which question?
The answer is
There always exists a solvable point?
yes. Well, for genus 0, of course, it's classical. For genus 2 and 3, it's easy to see you can find a map to P1 over the rationals of degree less than or equal to 4. And in genus 4, you can use the canonical embedding and view it as the intersection of a canonical quadric and a cubic in P3. And after a little work, you can see the result. Now I want to mention one other thing, which is the main point of his paper, which I'm not really going to discuss, but I'll just mention it for a reason that may become obvious. So he shows that if you change the field from the rationals to some other fields, then the answer is no. There are extensions where you have no solvable points. And the idea is the following. So the smallest one he gets is for g equals 6. And the idea is roughly as follows. So it takes several constructions, but this is typical. So you take the graph on 5 points. I guess you call it a complete graph or something. View this as a graph of P1s. And you have an S5 action. And because the degrees here at the vertices, missing one, the degrees at the vertices are at least 3, you can get a stable curve. And then you pick, and this is where it differs from the rationals, or indeed any number field. You pick a local field with an extension. So you pick an extension of local fields with Gower group S5. And then you can put an action on this over f prime in such a way as you descend it to f. So you find a curve over f. So this is not local, and this is just local in the sense of having a discrete valuation. This is not having a, it's not, so it might be something like power series in Cx or something. So power series over C. And that's the whole point, that for number fields, of course, the local fields of number fields don't, or localizations of number fields don't have non-solvable extensions. So but you find a situation where it does. Find a curve over f then with no points over f by descending, taking such a graph over f prime and putting on the Gower action and descent. And then you use, that's why I'm mentioning it, the Deligne-Mumford paper on the moduli space of curves of genus G to find a smooth curve over a discrete valuation ring where the residue field is the F here. And hence, since it has no points over the residue field, it will have none over the global field. So you get some construction, which he found for genus 6 and some higher genuses, not actually for genus 5, but obviously the method doesn't work for Q or for any number field. Okay, so what I want to talk about in this talk is genus 1. So let me, to make it completely clear, since I, for one, am so used to working with elliptic curves, I'm going to distinguish curves of genus 1, by which I mean curves of genus 1, and elliptic curves. So here's an example of one. Now it's Jacobian, In this case, it's a well-known example. Its Jacobian does have a rational point and always will have a rational point, but the original curve may not have a rational point. And this is an example. In fact, what was famous about this example is that this has local points in every QP, but no rational points. Okay, so this I'll refer to as curve of genus 1. This one I will call, when it has a rational point, I call it an elliptic curve. So one of the interesting things about genus 1 curves is if you just try and find a map to P1, and you might ask for the minimum degree of a map to P1, well, your first obstruction is that even locally you may fail to have points. So you may have some obstruction there. But even if you have local points everywhere, it's conjectured that this degree, this minimum, is unbounded. I'm not aware that it's been proved, but in general it's not so hard to find it to find arbitrarily large degrees if you don't require it to have local points. Okay. Okay, so now what I want to do is I want to just review what's been done for elliptic curves. This is actually relevant to the calculations on genus 1 curves. At first sight, it's not obvious why finding points on an elliptic curve would help you with a genus 1 curve, but it does. So first, the first theorem, of course, is the Moore-Delvey theorem. If you have an elliptic curve, then over any number field, the group is finitely generated. It has some finite rank, G of F. It's a finite abelian torsion group. So that's for F. A number field, particular for the rationals. But it's an unsolved problem how to construct these points or to determine GF. So the main technique has been understanding the L function. So I'll just remind you about this. So we can define the partial L function of E as the product of the primes not dividing the discriminant of the curve of 1 minus AP norm p to the s plus norm p to the 1 minus 2s, where AP norm p minus AP is the number of points over the residue field. And the conjecture of Birch, Swinnerton, and Dyer says that first this should have an analytic continuation, and then that GF should be given by the order of vanishing at s equals 1 of that analytically continued function. Okay, so the results so far on this can summarize at least over Q. Let me say it first over the rationals, so that's F equals Q. The theorem due to several different people. So if the L series does not vanish, then GF is 0. So Coates and I proved restricted cases of these when E had complex multiplication, and Kolyvagin proved it in general, and Kato has given a second proof of that. If the L series vanishes and the derivative does not, then the rank is 1. It's due to Gross-Sagier. Gross and Sagier. And if the L series vanishes and the derivative vanishes, then nothing is known. Moreover, in case 2, Gross and Sagier actually give a construction of a point of infinite order. Not in general the generator, but at least a point of infinite order. So let me just remind you of that construction. So one starts off using the modularity of elliptic curves. It implies there exists, or one way of stating it is that there exists a map defined over the rationals from the modular curve x0 of n for some n to e. So x0 of n, of course, is just the quotient of the upper half plane by gamma 0 of n be rectified. So gamma 0 of n is the usual subgroup of SL2Z. And x0 of n can be described as the moduli space of elliptic curves with a subgroup of order n, so that we can view a point in the upper half plane as giving rise to an elliptic curve C mod tau 1 with a subgroup 1 over n. So what we want to do in this case is we take k imaginary quadratic, we might take, so then what we want to do is take C mod the integers of k, and we want to restrict k such that every prime dividing n splits in k. So p equals p bar in k, or in the integers of k, for all p dividing n. So that is a requirement on k that we're going to make, because then we can take, that implies that n splits, and we can then take the kernel of n as our subgroup of order n. So the theory of complex multiplication tells us that this is actually a point of x0 of n defined over the Hilbert class field of k, maximal unramified extension of k. Okay, now you can map this point. So let's call this P, map P. That gives then a point over H of the elliptic curve. And then we simply take the trace down to K of pi of P, and that will be in EK. And the whole problem with this construction, which in some sense a lot of it goes back to Heegner, the problem is you have no idea whether this construction has given you a torsion point or a point of infinite order. Very often it will give you a torsion point. So the theorem of Gross and Zagier gives you conditions under which it is of infinite order, so you have to make a further restriction on k. So if you have to arrange it so that, well, we're assuming for Gross-Zagier, that is in what I had as situation 2, which was that the L series V is 0, but the derivative is not 0. you also have to assume that the L series of E twisted by the character corresponding to K is non-zero. In other words, that the L series over K, rather than just over Q, vanishes to the first order also. So the existence of such Ks, also with the splitting conditions, is a theorem of Wiles-Bourget. So this, such a K exists. And under these circumstances, Gross and Zagier prove that this point, trace of pi of P, has infinite order. So this use of CM points is the only general method we have for proving the existence of points of infinite order over fields that we care about, at least.
What do you do about field of definition? Did you assume class number was 1?
No, I'm taking the trace.
Oh, it's the sum of the conjugates.
The sum of the conjugates, yes. That's why it's hard to tell whether it's got infinite order. When you take the sum of the conjugates, it's very hard to see what happens. Yeah, by trace here, I mean the trace on the elliptic curve. So it's the sum on the elliptic curve of the conjugates. And the way it's set up, if I started with the L value 0, and I chose that there was no point here, then this is actually essentially a rational point rather than just over K. So this has been much generalized. By Gross and Zagier themselves. So there, one wants to generalize in the sense of taking abelian extensions of K and then getting more points over those extensions and checking that different eigenspaces under the Galois action are filled up by these points. So by Gross-Zagier, that's abelian extensions of K, at least certain ones, not all. And also by Zhang, who showed how to replace the whole theory, which here is over the rationals, with a theory over any totally real base. And here you have to use Shimura curves rather than modular curves. Okay, but basically this method seems to work whenever the rank you're aiming for is 1. So then you seem to find your point by using CM points, but only when the rank is 1. When the rank is bigger than 1, the CM point construction of Heegner always seems to give you 0. So this method is actually analytic in the sense that although the construction, of course, is a piece of algebra, but checking it, you do that by relating the derivative of the L function to the height of the point. So if the derivative is non-zero, then the height is non-zero and the point is not torsion. But it actually uses the L series explicitly. And some of the points here are very technical, and it means that the generalizations and some of even the original theorem only actually operate in slightly restricted circumstances. So I want to just now mention a different method, still with CM points, but solves a different problem, which is the following. Supposing rather than trying to get a specific point, you're interested in getting points over, say, the cyclotomic, anticyclotomic ZP extension. So K infinity is anticyclotomic ZP extension of K. So the anticyclotomic extension is one in which, so you have K over the rationals, have a Galois group, which is ZP, in which the Galois group of K over Q acts like -1. Instead of being abelian over Q, it's dihedral over Q. So then one uses the same kinds of points. So now we use what are called the ring class fields. So again, we have an imaginary quadratic field, and we can use the ring OC, which is Z plus some constant times some integer times the integers. So this is a subring. And you can now look at the point constructed from this, C mod OC, and again you want an n that splits, so we have some subgroup. And you can do the same thing, try and look at the image, and the same kind of principle works for these, the Gros-Sagier method, but what they want to do is something slightly different. So they ask, supposing you take all C's, say all p power C's, so take C equals p to the n going to infinity. Then, supposing you take this construction, supposing we look at the trace from the field H infinity, which is H adjoin K infinity, to K infinity, of the point pi of yp to the n. So y of p to the n lives in H adjoin, it's actually a ring class field of conductor p to the n, so H infinity will be this union of the ring class fields of conductor p to the n. Which am I right? So these are some abelian extensions. Of prime power conductor. And you can ask, and they asked, actually Maser asked, this was a conjecture of Maser, supposing you take the trace of these, do you get points from these? That is, for some sufficiently large n, do you actually get non-vanishing? And they indeed proved that the trace is non-zero for sufficiently large n, for some large n, and then actually one can deduce it for sufficiently large n. So that's the theorem. What this is saying is that the generic situation, if you set yourself up right, is to be in rank 1, or if you set it up wrong, it's in rank 0, but if I'd set it up right, so it's the same setup as before, then eventually you do get points by this use of CM points. You do get points of infinite order. So, sorry, I should say is not torsion. Their method is quite different. What they do is they take a prime that's inert in K, and they simply look at everything over the residue field at Q. And the idea is that the group EK infinity torsion is actually a finite group. There's very few torsion points, even over this big field K infinity. And since pi is a finite map, there's only finitely many points of x0 of n even above them. So the idea is they will actually look at these complex multiplication points, and by knowing the Galois action, can actually see there are so many points they can't fit into that finite set. It's actually a very subtle argument and uses a theorem of Ratner, homogodic theory, to actually accomplish this. So it has a quite different source from the Gross-Arguer theorem. It actually works with less restrictions than the Gross-Arguer theory. Obviously, it's giving a less fine result, and it's just saying you find a lot of points rather than a specific point is of infinite order. Okay, so now back to curves of genus 1. So that's what's known about points on elliptic curves. And as you see, almost all the points that we know about actually come from CM points. And as far as we understand it, you obtain them precisely when your rank in some eigenspace is 1. In the general case, we don't know any construction. So supposing we have a curve of genus 1, let's call it C. The Jacobian of C is an elliptic curve E, which of course does have rational points. Then, of course, C does have points over some number field, at which point these become isomorphic. So C is a twist of E, and we can actually view C as giving us then a class in the cohomology group. Well, the standard theory of twisting would actually give it in the H1, the set H1, the Galois group, acting on the isomorphisms from C to itself. But its old result, I think, is due to Châtelet, I'm not sure. But you can actually view it as giving a class in the cohomology of E. E can be viewed as isomorphisms of E with itself, namely if you take the curve underlying E and add a point, that gives you an isomorphism. So this is a subgroup of the group of isomorphisms of E. And we actually get a class in here. So this is the first fact. And the second classical fact is that C, this class, is 0 if and only if C has a rational point. Neither of these are hard, but okay, so now the standard descent theory in elliptic curves. You start with the operation of multiplication by p, gives you a short exact sequence, and from it taking Galois invariance and a long exact sequence we get. And I'll now abbreviate cohomology of q bar over q by h1q and the kernel of p in eq bar by ep. And similarly, eq bar by e. And if one had an extension field, one would have similarly a sequence for L, the same kind. And what we're trying to do, so according to classical theory, to find a rational point, all we have to do is make sure this class corresponding to C goes to 0 when we take some solvable extension L. Well, we can lift this class to a class H1Q EP, and we can try and find an L such that when we pass to restrict to L, the class vanishes there. Well, at least not vanishes. We want it to vanish when it goes to here. In other words, it should be the image of a point. So in other words, what we're trying to do is find points over solvable extensions which cover these classes. Now, of course, the image of a class here will be Galois invariant, so what we really want to find is images of points here which give Galois invariant cohomology classes. So one thing to try is simply to take all classes coming from these CM constructions and this has been studied in great detail by Kolyvagin, studied the cohomology classes and in particular when you can descend them to classes over Q, and he constructs many classes this way. I don't think one expects to get all classes this way. But one has a construction of many classes. So how does that help? Well, I want to use a principle that actually was central to the Fermat paper, perhaps implicit in Kolyvagin 2. And that is, supposing you have a number field, one of the most mysterious and important problems is to understand the Hilbert class field of that number field. So if we take the maximal unramified extension of H, how do we find it? What can we say about it? Well, one very general but quite simple principle is that if you take all the tamely ramified extensions of F, that if you find extensions which are tamely ramified at different primes to the maximal amount that would be allowed locally, then already inside these fields that you generate that way, you would already have the Hilbert class field. And somehow it's trapped by the tamely ramified extensions. So it's not a very, I'm not making it very precise, but it's been a very useful principle that if you can construct extensions where you can see the ramification and it's the maximum amount you might find locally, so you know the maximal size of a local extension of F, tamely ramified at prime Q, say, that if you can do that locally for sufficiently many primes, then you've already contained H. And I mean contained group theoretically. That is, if you constructed these extensions, then this will be a sub-extension. Okay, well, the same kind of principle works in this setting. And what it says is that the Selma group, so while we can't expect to generate all of H1 QEP, we can hope to generate all the classes in the Selma group. And one way of saying what the Selma group is it's the inverse image of classically the Tate-Shafarevich group, or in the language I've been talking, the C is such that CQP is non-empty for all P. So the twists of E, which have points locally everywhere, give you some classes. The ones that are inverse images of those you can regard as the Selma group. So here, this is lambda P. So that will give you part of the Selma group for order P. So in some sense, this is the analog of unramified classes. They're not quite unramified, but they're as unramified as we can deal with. Namely, if we construct many classes where we do have ramification, we may not get all the ones with ramification, but we should trap these ones. So using this method of Cornu and Vatsal, which actually show that somewhere out there are points, you can make this Kolyvagin construction. Using that, we are able to prove this following theorem then. So if C is of genus 1 over Q, and so the restriction here is that there are local points everywhere. And then one more technical assumption for this is that the Jacobian should be semi-stable, the original elliptic curve. Then C has solvable points. Now these conditions are quite restrictive. On the other hand, they're beautifully designed to disappear under base change. So these conditions can be removed by a solvable, totally real base change. So then one would hope to go up to a totally real field where both these conditions can be met and apply the same technique over the totally real field. And while I don't envisage any difficulty with this, we haven't written it out, so I don't know that it works, but it seems to me that one can that way prove that there are rational points over solvable points for any genus 1 curve. So I don't think one can use these CM points just coming from the ground field. I think one has to make such a base change for this reason that I don't think you get all the classes just from CM points. I think you really have to you're only getting the classes that correspond to the inverse image of the Tate-Shafarevich group. So for genus 5 or bigger, I have no idea whether there are solvable points or not. Some experts tell me they believe that there are, but I've seen no evidence either way, so I don't know what to say. But I think it may be a problem to hand back to the geometers. So I'll stop there.
Questions or comments?
You can remove both conditions, I and also the condition I.
This one? Yeah.
What does this say in terms of non invariance?
I don't know. Could we ask Malin? I don't know. I'm not an expert. Yeah.
For totally real field, what is the analog of the Higgs point construction?
So you use Shimura curves and you use CM points on Shimura curves. No. This has been written in great detail if you want to look at by Zhang and a student of his named Tian.
Do you get a bound on the length of a solvable series for the Gaussian extension over which you're trying to come?
Yeah, I think you see, if you have these conditions, then over K, it's just going to be abelian. If you have to make an extension and assuming it worked, to cover these two problems, I think it's just abelian there. So you go K, so it's abelian and then abelian, I guess. I think that's all.
Is it known that there's not always a point in an abelian extension?
Is it known? There's not always a point. No, I think very little is known. Is it known? It's a good question. Is it known that there's not always a point in an abelian extension? No, not to me anyway.
Any other questions? Yes?
Can you see if somebody hands you a curve which you know is genus 1, can you then construct a point?
I haven't checked, but I assume that the Ratner's theorem is not effective, but maybe Peter knows. I'd be very surprised if this were effective.
Usually the rate is.
You think it would be?
I think there's another proof also that makes allows to show that which avoid, for that particular thing, which avoid Ratner that use some version of this Andre Ort, but maybe that
Yeah.
can be discussed.
I haven't checked, but I'd be a little surprised. It's quite hard to tell when you start getting non-vanishing of derivatives in general, just from an analytic point of view. And if this is another way of finding it, then
I might point out that in the Rorley case, where you take a cyclotomic rather than an anti-cyclotomic, then you can handle everything very easily, but of course you don't get points. So this is the beauty of the anti-cyclotomic, which analytically seems to have a range.
Yeah, I just point out the obvious that if C doesn't have points over R, if P can't be infinity, if you have a genus 1 curve without points over R, then a totally real base change won't help you.
you're right. Well,
So you sort of have to assume that C has points over R to make that statement.
yeah, I guess for the reals, I mean, in some sense, one's only going to make points over CM fields anyway. Yes, I'm sorry, I haven't thought about R. I think one has to state it more carefully. Yeah.
Put it 0.
So, can you get then points, suppose that you have a hypothesis I and double I, can you get also points which are, say, totally dyadic and dyadic and dyadic?
So you can certainly make them split completely at any prime that's not part of your problem. So prime's not dividing n. You could do that. Actually, these points obviously are not going to be real. But there's actually an extremely interesting conjecture of Darmon that suggests there's a whole theory of, instead of CM points over abelian extensions of real quadratic fields. And if his conjectures were true, it wouldn't surprise me if you could do something. I mean, you've got this problem maybe that you can't find real points locally, but after that, if that were allowed, then maybe you could. I'm not sure. But that's the most interesting thing, is whether you can do them, I think, over real fields rather than p-adic ones. But,
What do you expect the structure of the group of points over the maximal solvable extension to look like? In fact, would you expect it to be infinitely many points then?
oh, the rank will be infinite, but I mean, I don't know how to gauge what size it is. Usually, even over these, what is part of this theorem of Cornu-Vatzal says that the rank is infinite even over this ring class field ramified at just one prime, or prime above P. So I'm not sure what more to say. I mean, there'll be many more points, but I don't know how to say how many there are.
Any further comments or questions? Great, let's thank the speaker again.